Okay. Good morning or good afternoon, and happy birthday to Yuri. And thank you for inviting me to this fest. And I'm glad to talk about this topic, Rabin uniformization problem with restricted domain variables. And there are some reasons for this. First of all, Yuri and Shelach studied Rabin uniformization problem and provided solution to it. Next, they used compositional method, and I also will use compositional method. And finally, Yuri taught me to use compositional method and taught me to use compositional method. So this is my talk for this fest. Uh, no, so I will sorry, something wrong. So here's plan of my talk. I will explain what is uniformization. I will explain what is Rabin uniformization problem and explain solution to this problem provided by Yuri and Shelach. Then I will state main results and try to provide proofs or sketch of proofs, and finally I state some open problems. Consider relation R here, and a uniformizer for relation R is a function. So I am taking X and I'm looking to all elements which are related to X. This is cross section at X, and a uniformizer choose one element from every non-empty cross section. So uniformizer for relation R is a partial function with the same domain as R and which is included in R. So on this picture, uniformizer is blue line. And obviously, the axiom of choice implies that every relation has a uniformizer. And we say that a class of relation R has the uniformization property if every relation in this class has a uniformizer in this class. And important topic in the descriptive set theory and the recursion theory was what classes of relations have the uniformization property. So in this talk, I will consider monadic second order logic over the full binary tree. So monadic second order logic is extension of first order logic by set variables and quantification over sets. I will use capital letters for set variables and small letters for individual variables. And Rabin proves that monadic second order logic is decidable over the full binary tree. So this is celebrating result, and a lot of other decidability results are easily reducible to Rabin's theorem. If we have monadic second order logic with two free set variables, it defines a binary relation on the subset of the full binary tree. And Rabin asked whether the set of monadic second order definable relations over the full binary tree has the uniformization property. That is, for every formula phi, there is another formula psi such that the relation definable by psi uniformizes the relation definable by phi in the full binary tree. And Gurevich and Shellac provided a negative solution to Rabin's question. So let me describe the solution. A choice function chooses one element from every non-empty set. Hence, it uniformizes a relation y is one element subset of x. And Gurevich and Shellac proved that there is no MSO definable choice function in the full binary tree. There is no MSO, so there is no MSO definable uniformizer for relation y belongs to x. Therefore, the uniformization property fails for monadic second order definable relations. And the proof of this theorem is remarkable and quite difficult. So this theorem deals with combinatorial objects, automata on a trees. So relations on a full binary tree are defined by automata. But to prove this theorem, Gurevich and Shellac used forcing method and other set theoretical method. So the proof of this theorem, original proof, was very difficult. And alternative automata theoretical proof was obtained about 30 years later. In view of failure of uniformization, it is natural to ask the following question. Decide whether MSO definable relation has MSO definable uniformizer. Unfortunately, we were unable to solve this question, and we consider much modest question to provide sufficient conditions for when formula has MSO definable uniformizer. So this question we will address in the rest of the talk. Uniformization fell for MSO formula of the form phi xy. So formula y belongs to x is of this form, and here the domain variable x is unrestricted. It ranges over arbitrary subsets of full binary tree, but the image variable range over one element sets. And does the uniformization property holds for formula of the form phi xy, where the domain variable range over one element sets and the image variable is unrestricted? And it turns out that this formula have uniformizers. Consider the formula of the form phi pi y. Here, the domain variable pi range over branches of the tree, and image variable range over is unrestricted over arbitrary subset of tree. And it turns out that also these formulas have uniformizers. And now we are going to restrict to domain variables, and one of the way to restrict domain variables is to use Cantor-Bendixson rank of a tree. So I will recall what is Cantor-Bendixson rank. If I have a tree, I can take a derivative of tree. So derivative of tree t removes a node if the set of its descendants is finite, or the set of its descendants is linearly ordered. We can iterate this operation. We can define second derivative, third derivative, and so on. And Cantor-Bendixson rank of a tree is defined as follows. Tree has rank k, if its k derivatives is an empty set, but k minus first derivatives is not empty set. Oop. Oop. Consider this picture. Here, the root is in the bottom left corner, so this is a tree. The left sum, or consider left sum of the root. So this set is linear ordered. So by taking derivatives, we remove left sum of the root and all its descendants. Consider the right sum of the root and its left sum. Here we have a finite set of descendants. Therefore, first derivative removes all these nodes, all these three nodes. Consider the next sum. So this sum with the left node, the left sum has again linear ordered set of descendants. Again, first derivative removes all those nodes, and so on. After taking first derivative, what is left? We have a root and we have horizontal lines of right successor of root. And this set of nodes is linear ordered. Therefore, taking one more derivative, we obtain the empty set. So the tree in the picture has counter-Bendixson rank 2. And here is a restriction of sets which we call simple sets. A subset of full binary tree is k-simple if there is another set which contains it, which is downward closed, and the counter-Bendixson rank of the set is at most k. And here our main result. For every finite k, if the domain variables of phi, if the domain variables of formula phi are restricted to k-simple set, then phi has the uniformization in the full binary tree. Example, consider a branch. A branch is downward closed already, and its counter-Bendixson rank is 1. So a branch is one simple set. A vertex. A vertex, if we take downward closure of a vertex, we obtain a path from the root to the vertex. This is a finite set of nodes. Therefore, its rank is 1, and therefore a vertex is one simple. If we consider a finite set of vertices, by the same argument, it is one simple. So, for example, from our theorem, it follows, if you take k is equal to 1, then it follows that when domain variables are restricted to finite set and branches, then such formulas have uniformizer in the full binary tree. Another lemma or theorem which plays an important role in the proof, I will explain it now, but it has an independent interest. So counter-Bendixson rank measures the branching complexity of a tree. That theorem says the following: the uniformization for every k, the class of binary tree of counter-Bendixson rank k has the uniformization property. So here we talk about property of the class of tree. So I will explain when such class has, what does it mean that the class has uniformization property. If a formula psi uniformize formula phi over class C of structures, if psi uniformize phi in every structure in this class, and a class has the uniformization property if for every formula phi there is a formula psi such that psi uniformizes phi over the class. So to sum up, so our main result are the following one. The class, for every case, the class of binary trees of Cantor Bendixson rank K has uniformization property. And if in the full binary tree we restrict domain variables to range over K simple sets, then this formula have uniformization property. And now I can move to proofs or sketch of proofs. Any question about results? Okay. So I'm going to prove sketch. So I will sketch the proof that the class of binary tree of Cantor Bendixson rank K has a uniformization property. And I will proceed by induction on K, and basis is K equal to 1. In this case, a tree has Cantor Bendixson rank 1 if it is either finite or isomorphic to omega. On finite tree, it is easy to find uniformizer for formula phi. So we can order a subset by lexicographical order. So this is linear order on subset, and every set of subset has a non-empty set of subset has a the minimal element. So uniformizer for phi xy will choose the minimal y which satisfies phi xy. Over omega also has the uniformization property, and it was proved by Lifshitz and Scheller. So we finished proof of basis, and for inductive step, we will use that derivatives are derivative of 3 is MSO definable, and some elements of compositional method. So in the previous talk, Sven mentioned compositional method, and in his talk, a complex structure was constructed from simple one by concatenation or by sum of linear orders. For tree, we need other operation, and this operation is called grafting operation. So I will explain this operation, which will produce a more complicated tree from simple tree, and then the logic about complicated tree can be reduced to logic about its component. So suppose T is a binary tree, not full linear binary tree, just a binary tree, and G is pair function. G left is a map that assigns to nodes without left child a binary tree, and G right also assigned is a map which assigns to nodes without right chain a binary tree. So to different nodes, different binary trees are assigned. And it is not necessary that a binary tree is assigned, G left assigned to tree to every node without left child. To some node without left child, G left assign a tree. So this is function, and then given such G, the grafting of T according to such pair function G is a tree which is obtained, denoted by GT, is defined in the following way. So consider here black tree. So suppose, so this node in black tree has no left child, and suppose G left assigned to this tree such a subtree. So what we are going to do, we add to this node left child, and make it the root of the tree assigned by G left to this node. Also, this node has no left child in the black tree or in black tree. So, and suppose G left assign this subtree to this node, then we add one left child to this node and make it to be the root of the tree assigned by G left, and so on. So this is the result of applying G to a black tree. So what we have a black tree, and then to some of its nodes, we added sons, which has the root of tree assigned by G. So here is a theorem that uniformization property is inherited by grafting. So let me explain this theorem. Assume that T has, I start from a tree T, which has a uniformization property, and suppose C is a class of three, a set of three, which also have uniformization property. And G is pair function such that the image of G are inside of C. Okay. Then what I claim is the following. Construct a complex tree obtained by applying grafting to our original tree T. Now we expand this complex tree by monadic predicate, which is a set of nodes inside T. So we obtain our labeled tree, and the theorem states that this structure has a uniformization property. If you are going back to our example, again, suppose this black T has the uniformization property, and suppose the set of all red trees has uniformization property, then theorem says that the tree we constructed and which is expanded by a unary predicate which contains all nodes of our original tree T has a uniformization property. And as corollary of this theorem, we obtain that if a tree has counterbendix on rank K, then it has a uniformization property. And again, we proceed by induction on K, and the inductive step is the following. Suppose I have a tree T prime of counterbendix on rank K plus 1. I can consider this tree as obtained by grafting on its derivative T. So if T is the derivative of T prime, then T is obtained from T prime by removing nodes with finite number of descendants and nodes with linear order set of descendants. And other way around, we can consider T prime as obtained from T by grafting to some nodes finitely many finite tree, or to some nodes a tree isomorphic to omega. So, okay. So, of course, T is MSO definable in T prime, and by definition, counterbendix on rank of T is K. Therefore, by inductive hypothesis, T has uniformization property, and therefore, by our lemma, T prime, this is G of T, expanded by nodes for T has uniformization property. But nodes of T are MSO definable in T prime. Therefore, T prime has the uniformization property. Okay, so this is our main lemma, main proposition, and it is proved by compositional method, but it will take too much time, so I will prove another theorem, another proposition by similar technique. So let me recall what is selectors. Formula psi is a selector for formula phi in a structure M if either both are unsatisfiable in M or there is exactly one element y which satisfies psi and this y also satisfies phi. So selector is like a uniformizer but without domain variables. So selector from every set choose one element. And M has the selection property if every formula satisfiable in M has a selector. And the Rabin basis theorem says the following: the full binary tree has the selection property. Rabin stated in different way. He stated that if a formula with one free variable satisfiable over a full binary tree, then it is satisfiable by a regular y. Yeah? Yes, but regular y's are MSO definable. So the full binary tree has selection property, and probably the reason Rabin asked for the uniformization of the full binary tree is that tree has the selection property and was not clear whether it has the uniformization property. Now I will recall some elements of compositional method. So if we consider formulas in fixed relational signature with fixed set of free variables, then there are finitely many formulas of quantified depth at most n. And theory n of t expanded by predicate z1, zn, or n theory of t, is a set of such formulas which are satisfiable in phi. So theory n is infinite object, but it can be characterized. There are, first of all, there are finitely many possible n theories, and every n theory can be characterized by one formula. For every n theory th, there is a formula tau of quantified depth n such that theory n of 3 equal to th if and only if this tree satisfies tau. And this tau is called the n-type of a tree. And the set of n-type, no, we denote by type n the set of n-type, possible, formally possible n-type, and this set is computable. Now I will state a compositional theorem for grafting. Suppose G is pair of function and T is a set. Suppose grafting for this tree, and so then the type n of G is a mapping into type n. So every they with the same domain as G, but for every node V, image of V will be the n-type of the corresponding tree. So I forget what tree was assigned to V, and I remember only the type of this tree. And V compositional theorem states the following: assume that G is a grafting for T, then theory n of composite tree GT is determined by T and type n of G. So in order to know n theory of complex tree, it is enough to know T itself, basic T itself, and the n type of trees assigned to by G. And the composition theorem is a little bit stronger or much stronger, and it states the following. So assume that there are m possible n theories, then compositional theorem state for grafting states the following. Suppose I have formula phi xy is two free variables of quantified epsilon. For this formula, I construct another formula psi, which has variable xy like original formula, and then for every possible n type, it has a set variable or monadic predicate variable. And then the following happens. If I want to check whether formula phi holds in complex structure or in grafting of t of z on t, then what I have to do, I have to look to my original simple 3t. I look to restriction of interpretation of x and y to t, and I'm looking to type n of grafting functions. And then if this whole story satisfies psi, then phi holds in the original tree. Actually, if and only if. So we reduced formula which talk about complex grafting tree to formulas which talk about much simpler trees. Okay. And here is a theorem. It says the following. Suppose C is a class of binary tree which has the selection property. If the domain variable, suppose I have a formula with one domain variable. If the domain variable of phi is restricted to downward closed set in this class, then phi has uniformization in the full binary tree. So we assumed here selection property for one domain variables and deduce uniformization in the full binary tree. And again, the proof of this theorem is not difficult. It can be explained on one slide here explanation, but I skip this explanation because probably it is difficult to follow them. Okay, so as conclusion of this theorem, we obtain that for every k, if the domain variable of formula phi is restricted to downward closed set of rank at most k, then phi has uniformizer in the full binary tree. And this follows from the fact that class of binary tree of rank less than k has the uniformization property. And here we require only selection property, which is much more weaker in the previous proposition. And this theorem holds when we replace, instead of one domain variable, we take several domain variables, and instead of downward closed set, we take a k-simple set. But this extension requires that we have to, the domain variables are restricted to k-simple sets. Okay, so let me explain some further result. We prove that for every k, the class of binary tree of counterbendixson around k has the uniformization property. Let C be finite be the class of trees of finite counterbendixson rank, and C counterbendixson diff be the class of tree with definable counterbendixson rank. So it's the same a tree has definable rank if it has only countable many branches, or equivalently if the full binary tree cannot embed it inside T. And the natural question is, does the class of C be finite has the uniformization property. So for every k, finite k, we prove that this class has CBK has uniformization property, but we don't know whether the uniformization property holds for the whole class, union of. Another question, does this class has definable choice function? Or does this class has the selection property? And one can easily show that if C uniformize phi over class of counter Bendixson tree of finite rank, then C uniformize phi over class of tree with well-defined rank. And also one can show that if counter Bendixson, if the class of counter Bendixson tree with finite rank has the selection property, then the class of counter Bendixson tree with definable rank has even uniformization property. So we believe that the answer to all of these three questions is negative, but we don't know how to prove it. And the main question remains open. It is decidable whether MSO formula has an MSO definable uniformizer over the full binary tree. We have no clue how to solve this question. A related problem about ordinals was answered positively. It is decidable whether MSO formula has an MSO definable uniformizer over the countable ordinal. And over countable ordinal, the uniformization property also fails, but we succeeded to provide algorithm which decides whether formula has uniformizer or not. Happy birthday, Yuri.